Well, chemistry students, it's time to buckle up. Make sure your safety helmet is on because today we are continuing on that journey which will lead us to an awareness of the periodic table, an understanding of the periodic table, a releasing of the secrets contained on the periodic table. We are on that journey to a greater understanding of the subject of chemistry and the foundations of which this subject is built upon. Up to this point in time, we've been working with Model 4, Bohr's model of the atom. And if you remember, Bohr's model of the atom was the one with the 7 energy levels on it. And we already learned that the first level holds 2 electrons, and the second we could put 8. The third, actually, we now know can go up to 18, but it was stable, chemically stable when there were 8, etc., etc., etc. But as we've began to take a look at Schrodinger's 5th model, called the quantum mechanical model, also called the electron cloud model, we know that Bohr's idea of energy levels was only the tip of the iceberg. We now know that each of these energy levels are made up of one or more sublevels. Bohr assumed that every electron on a particular level had the same amount of energy, and we now know that is not true. The electrons on the first energy level do have the same amount of energy. The electrons on the second level have more energy than the electrons on the first level. Yet not all the electrons on the second level have the same amount of energy, because we now know that the second level is made up of an S sublevel containing 1 orbit and a P sublevel containing 3 orbits, and the electrons in the P sublevel have slightly more energy than the electrons in the second level in the S sublevel, which we would call the 2s. The 2p electrons have a little bit more energy than the 2s. The third level, the electrons on the third level have more energy than the electrons on the second level. But not all the electrons on the third level have the same amount of energy, because we know the third level is made up of 3 sublevels. An S, which contains 1 orbit, a P sublevel, which has 3 orbitals, and a D sublevel, which is made up of 5 orbitals. The D sublevel has more energy than the ones in the 3p. The 3D has more energy than the 3p. The 3p has more energy than 3s, and these are the things that Bohr did not know, but which now explain these bright line emission spectrums of the larger atoms. So away we go into the 5th model of the atom. And today we're going to begin talking about how to represent electrons and the placement of electrons in an atom according to Schrodinger's quantum mechanical model. We no longer can just draw circular orbits, because we know there are not flat 2-dimensional circular orbits. We know they are 3-dimensional orbitals. And now we have going to learn how to draw those and hopefully gain a better understanding of Schrodinger's model. And from that, folks, get ready. You'll never be able to look at the periodic table quite the same. Today, we will be looking at the 4-8 notes, and we will also go through the 4-8 practice problems so that you have some understanding of what you'll be asked to do on 4-9. Once again, you do not have to watch all these videos back to back to back. There will be multiple videos on 4-8. You can watch one and go on and do something else. Watch another. Go to another class. That's the beauty of these videos, is that you can watch them, and when you know that your brain is telling you you've had enough, you can take a break. As we mentioned, we want to start to learn to draw electron placements in the atom using the 5th model. When we're trying to represent where electrons are, in general, with the 5th model, they're called electron configurations. It is a general term for showing where electrons are in an atom. And when you know where the electrons are, you'll begin to be able to say more about the behavior and properties of those elements. and you'll come away with a much greater understanding of the mysteries behind the periodic table. We know that each atom from different elements have their own unique numbers of electrons. Therefore, each element has its own unique electron configuration, different from every other element. In Unit 4-8, we're going to learn 4. It says in your notes 3, but we're actually going to be learning 4 different ways to show where electrons are in an atom, following the principles of the 5th model of the atom. The first one that we're going to deal with today is called orbital notation. Then we're going to learn to move into electron configuration. So there is an electron configuration. So in other words, an orbital notation is a way of showing electron configurations. One of the ways of showing electron configurations is actually called electron configurations. A third one that we're going to learn to do is called noble gas notation. It's also called compressed or condensed electron configurations. And then the fourth one that you might want to add into your notes, which isn't here, but we will be learning it in 4-8, is called dot diagramming. So the 4 we're going to learn is an orbital notation. That's where we use lines or boxes to represent an orbital. So instead of actually trying to draw the shapes of the orbitals, remember the S is spherically shaped. The D's are sort of dumbbell or hamburger bun shaped. Or the P's are dumbbell or hamburger bun shaped. The D's look like 4 balloons tied together, or 4 Tic Tacs, or something like that. And then the F's are very difficult to describe, but instead of actually trying to draw the orbitals, we're going to merely use a line or a box to represent them. So the s orbitals, if you remember, the s sublevel was made up of one orbital spherically shaped. The further we moved out, the 1s had a small sphere, the 2s slightly bigger. On the third level, the s's keep getting bigger. Fourth would be bigger still. But we're not going to be drawing spherically shaped orbitals. We're just going to draw a box or a line to represent those. The p's were the ones that were sort of dumbbell shaped. One of the p's runs along the x-axis. That's called the px. There's one that runs along the y-axis. That's sometimes called the py. The one that runs along the p-axis is sometimes called pz. We're just going to put a box or line for the different p orbitals. The p sublevel, we would need 3 boxes if we were doing orbital notation. For the s, we would only need 1 box because there's 1 orbital. The d's, we're not going to try to draw all the d's during orbital notations and put little electrons in each of these. These are the 5 d orbitals making up the d sublevel. Instead, we're going to put 5 lines or 5 boxes. Remember, here's the f's. We're not going to try to draw all these f's out and put little electrons in there. We're just going to use a box or a line. We would need 7 boxes or lines for the f orbital. So orbital notations, we will actually draw something that represents the orbital, and then we know what the shapes are of the orbitals now that we've been introduced to Schrodinger's quantum mechanical model. For the electrons, we're going to use arrows. Electron configurations is really a shortened version of orbital notation, which we will learn later. Noble gas notation, also called compressed or condensed, is a shortened version of electron configurations. And then the fourth one, dot diagrams, is the shortest of all of them still. Some of you have done dot diagrams before. We will learn more about dot diagrams. We will add to your understanding of dot diagrams as you're now taking Chem 1. Regardless of any of the 4 ways of doing an electron configuration, there are some rules to follow. One of the first rules we have to follow is called Aufbau's order of filling. Aufbau is a German word which means building up from the ground, or building from the ground up. And Aufbau just says that electrons will always seek the lowest energy level, lowest energy sublevels that are available. Remember that the energy of an electron depends not only on what level it is, the lower the number, the lower the n, the smaller the energy, but also what sublevel it is in. So electrons will always try to go to the lowest level. So if there's No electrons on the first level, the electron will try to go to the first level. There's only one sublevel on that level, so it'll try to go into the S, the 1s. But if there's electrons already in the 1s, that electron will only be able to go into the second level of the atom. That's the next energy level. But on the second level, there's a 2s and a 2p. We learned that the 2s actually has a lower energy than the 2p. So if the 2s is open, that's where the electron would be found. It will try to go in there. The energy, once again, is the N plus L. Here they're doing a uppercase capital L, but remember it's supposed to be like a cursive L. How do I know that the S has lower energy than the P? The P's lower energy than D. The F sublevel, made up of 7 orbitals, has the highest energy. Remember, these are the letters that the spectroscopist picked for the different sublevels. The actual quantum number, L when you're in the S is 0. L when you're in the P is 1. L when you're in the 2 is D. L when you're in the 3 is F. So on the second level, an electron in the 2s would have an energy of 2. 2 for the N, 0 for the S. If it was in the 2p, the energy of that electron would be 3. Second level would be 2. The L is 1. 2 plus 1 is 3. So electrons in the 2p have an energy of 3. The electrons in the 2s have an energy of 2. That's something Bohr didn't understand. He thought electrons on a given level had the same energy, and they don't. So we will need to follow Aufbau's order of filling. They will always go to the lowest level, and on that level, they'll go to the lowest energy sublevel next. Remember what sublevels are on the different levels of the atom. The first level only has an S. The second level has 2, an S and a P. The third has 3, an SP and a D. The fourth has 4, an SP, D, and an F. The fifth has 5, an SP, D, F, and a G if it was needed, but it's not needed. The sixth has an S, P, D, F, a G, and an H. But on the sixth level, the F, the G, and the H are not needed. On the seventh level, there's an S and a P. Those are the ones that are needed. There's also a D and an F, a G and an H, and I think an I. Would that be 7? And then again, Aufbau's order of filling. The lowest level is a 1s. The lowest energy, N plus L, is the 1s. Then the 2s has an energy of 2. Then the 2p, remember when you're in a p, the second number is a 1. The 2p, 2 plus 1 is 3. The next one that would get filled would be the 3s. Why? When you're in the s, the second number is a 0. We're adding the N and the L. 3 plus 0 is 3. The 3p would have an energy of 4. 3 for the energy, the sublevel or energy level. The sublevel's energy is 1. L is the sublevel letter abbreviation. 3 plus 1 is 4. The 4s would be 4. Look at the 3d. The 3d's energy is actually 5. When you're in the D, your second number is a 2. 3 plus 2 is 5. So the electrons actually fill the 4s before finishing off the third level, the 3d. When we have a tie, for instance, the 4p also has an energy of 5, as does the 3d. When you're in the 4p, the p, the second number, is a 1. 4 plus 1 is 5. So 3d has a 5. So does 4p. Tiebreakers go to the lower end, lower first number. So a 3 is lower than a 4. So the 4p gets filled. The 5s's energy is also 5. When you're in the S, your second number is a 0. 5 plus 0 is 5. But it gets filled after the 4p because its energy is 5, and the tiebreaker is the lower first number breaks the tie. We're going to go on and talk about the other rules that need to be followed, the Pauli exclusion principle and Hund's rule, on our next video.